welcome to our next session of Fenceline monitoring. I'm Stephen Lazar with Atmosphere Optics. I'm the moderator for this session. And we have Dr. Abigail Koss, application scientist at TOFWERK USA in Boulder, Colorado. International PTRMS expert, extensive experience in environmental fieldwork for atmospheric chemistry. Research focal points include chemical ionization, development, and interpretation techniques, large mass spectrometry datasets. I'm going to send the sign-up sheet around. Somebody leave with it. Somebody who last time who's not signed up.
I have.
Okay, here we go. All right, thanks, Abigail.
All right, yeah, thanks. Right, so my title's a little vague because I only decided with you about a week ago what I was actually going to present actually about. So first and foremost, this is a story that I hope will be interesting. This is a story about the Suncor refinery, which is pretty close to me in Denver, Colorado. So my company, TOFWERK, plays a pretty small role in this story. I've tried to place our own scientific work in some bigger context. Secondly, technology featured prominently. I will tell you about PTRMS because I love PTRMS. So, and the third aspect of this is strategy. So this is a roadmap or a workflow. So with this modern instrumentation that's really high performance spectrometry real time, you get thousands of data. There's a way to measure nearly any kind of gas-based compound that you can possibly. So this is a workflow to figure out what's important when you can actually measure everything. And I'll show some different strategies for how we find compounds of interest in a really large data set, including both target and non-target compounds. So I'm not claiming this is the only way to work through a data set, but I do want to share my approach and my workflow. Main character. This is Suncor refinery in Commerce City. That's downtown Denver in the background. I picked this photo because you can kind of see this nice brown cloud haze blocking mountains. Because we have such a huge population center in Denver at a high altitude, really sunny climate, we're really sensitive to any kind of additional pollution that produces ozone. And because of this, and because the Suncor refinery is based downtown Denver, face a lot of scrutiny, probably a lot more than most guys. It also hasn't helped that in recent number of scandals. Do not want this to be your facility. Not a good look for anybody. Okay. This is the refinery, and it's immediately adjacent to some low-income residents. And the residents of these neighborhoods are rightfully really interested in pollution that is going on. But this area is really because there's a lot of different sources of air pollution. In addition to the refinery, there's highways with a lot of traffic. There's a wastewater plant, there's a cogen station, and there's a lot of smaller sources that have also proposed. And there's monitoring efforts that are in place to try to untangle. And these involve both regulatory groups and NGOs. There's a local nonprofit called pollutant that has a stationary monitoring site with some data that's available publicly in real time online. And on the regulatory side, Colorado House Bill 1189 requires that Suncor and similar facilities conduct Fenceline monitoring for specific compounds. In addition, this bill also provided funding for the Colorado EPA, which to buy a mobile laboratory for community air monitoring, and TOFWERK delivered this. So I was the project lead for this mobile laboratory, and this was my motivation in measurements in the area. The TOFWERK side, before I designed and delivered this mobile lab to see, I wanted to make measurements to test on figured out what the scientific payload should be. I'm also providing a lot of scientific support to CDPHE, that I can say something meaningful when I talk to them. And then the regulatory agency wants to answer who, what, and where types of questions. Who are the major emitters? Where are major compounds emitted from? And there's also a non-target aspect. So what sources and chemicals are there out there that we don't know about? Is a very small proton reaction mass spectrometer. So this is a lot smaller than the feature that we saw on the previous talk from Montrose. And for a lot of reasons, this particular instrument is maybe a little bit too low performance to do non-target analysis, but it has one really important feature that was relevant. So this is my 2002 Honda CRV. And here it is parked in my garage. I put together this mobile laboratory that cost significantly less than $1.5 million.
I like it.
I've got a sonic anemometer that I attached to the bike track mount on my roof. Zero air generator. I did get some pretty weird looks from my neighbors having this. We had about 3 hours of independent work. Okay. This instrument technique is a very popular approach, very closely related family of different called soft chemical ionization. Primary overreach. Ion molecule reactor along with ampere that contains the compounds that we want to measure. So instrument is volatile organic compounds in a few. This is a real-time direct measurement. Each observed peak that we see in the mass spectrum corresponds to one or more VOC molecular measurements that show commonly measured. So the time scale of the measurement, fractions of a second frequency, so we can get a really good map of where we're moving. Really small, a mobile lab. We did 7 drives last summer. And this map shows our drives in different colors for different days. We had really tried to do just about the same drive as second measurement. Looks like this. Each one of these red sticks, molecule present in here. And this plot is essentially abundance versus molecular weight. So with a data set like this, there's hundreds of compounds that are detected simultaneously. And the problem is how to decide which of these are important and how we actually turn this very complicated piece of data into action form. We've developed a workflow, a roadmap for how to approach mobile laboratory analysis. First, verify goals to make sure to understand the questions that we're trying to answer. And then we go through a couple steps of target analysis, looking at obvious target compounds, from known sources. And for each step, I'll explain what I mean by this. And I'll also give an example from our Suncor refinery study. And then we bring up to non-target analysis. So first, we search for chemically similar species from target analysis. Comparative analysis helps important compounds kind of pop out of the data set. Hotspots found in previous steps. Advanced techniques like machine learning to find patterns. I'll show one of these tests. First step is to clarify what we're after. So it's the same slide that I showed previously for study growth. And if we read between the lines, clear that there's certain types of compounds that are really, so specifically, we're after compounds that affect people directly. And this means they're toxics or producing substances. Interesting means that the compound is regulated. So there's a legal aspect to this situation. Interesting compounds also fall into one of these categories. And obviously, they actually have to be present here. Reproducible means that these compounds detected on many different days and different products. And as an additional result, we wanted to identify hotspots of interest. And there's non-target analysis. We're especially interested in compounds and sources that we did not expect. Target analysis is obvious targeting compounds. This includes legally regulated species. So, for example, these three are called out in the Colorado House bill. Suncor conducts its own Fenceline monitoring, and they detected this species, wondering about what it was. And also there were some species that were specifically requested by our clients that they're interested in. So we'll take a closer look at benzene in the next slide, but I also want you to remember this tetrachloroethane compound. This map shows benzene detected by a rural laboratory. Here's refinery and the wastewater treatment. So it comes here. And these different colors have been okay. So we can see that there's some spots where high concentration, but this is maybe not interesting because we found a spike there on only one day. So maybe we were behind a car with broken catalytic converter. On the other hand, hotspots that are really interesting day after day after day, enhancement of target compound. This one here is basically in the middle of the refinery, drive through the refinery on public roads, which is pretty incredible. And this is an unexpected point that we'll take a closer. For spots where we saw enhancement, some of these, other things, something that we communicate to our customer that they have. Closer zoomed in, binary hotspot. It's not referenced on here, but I'm encouraging. Comparison of benzene with a GC instrument that was stationed in this area. This is operated by Koss, a local nonprofit, and pretty amazing to me that this very small Hispanic outreach group has access to this instrument. I think this is a really nice illustration of how dark and mobile and stationary sites really provide complement. We can see that ambient background concentrations. But what's really interesting is the behavior of spikes. So we see that concentrations at a single spot over time. Concentrations can also change dramatically. But I really want to call attention to the y-axis graphs. This has a maximum concentration. From the mobile lab, it's a maximum concentration. Really shows you that if you're using long-term averaging, is we start to average out some of these high concentrations. In fact, it's really important. Next step is to define more target compounds given what we know about sources. Here's a few categories of sources that we know exist and relevant compounds that we come from them. So these particular categories and examples are from my own years of experience measuring air quality in Colorado, but you could also derive this kind of list by looking or looking at and we'll take a closer look at styrene enhancements. Map of styrene enhancements on all drives. Color is a different drive. So unlike the benzene map, styrene has a lot of little spikes everywhere. There is a hot spot, but these lots of little spikes probably come from a lot of very small local sources. We also see an enhancement. Is that both vehicle and refinery sources are really important for toxic. Of the compound list, we'll look at what I've called the usual suspects. So we know that we're particularly interested in air toxics and odor-causing compounds, and the species in this list are ones that often cause bad odor and are frequently targeted air toxics. The air toxics list is really easy to build because we published a list of ones that they were always interested in. The odorants list is built from published studies of odor landfills and farms and similar sources. I'll show you methane pile or methyl recount. I'm going to step through the maps of methane pile enhancement on each day. I want you to pay particular attention to the area right next to the window. Pretty terrible odor breeding compound around the wastewater plant. So this is probably a good fingerprint species. But it's also not the only source of methane pile. Right around here. Okay, so now non-target analysis. Unexpected compounds and hotspots, rather than looking for a specific already compound. So we've used 4 methods to find new compounds. So first, looking for chemically adjacent, then comparative analysis, and investigating hotspots, and finally positive matrix factorization. Target adjacent compounds. So, for example, from our target compounds list, which we developed in the first step, it's pretty clear that halogenated compounds are interesting. Nitrogen species are also of interest. So tetrachloroethene was at the top of our list because it's by Semaphor's own line monitoring. We could also take a slightly different direction for adjacent compounds. You know, there's like a legal or regulated aspect to this issue, so we could maybe think ahead to species that may be regulated years and kind of preemptively add these to our list. In the next few slides, I'll show you how we found. Okay, so let's first take a step back and look at our target compound, tetrachloroethene. And indeed, we did detect this during our drives. On at least a few drives, there were absolutely spikes in this compound area. So chlorine contains in mass spectrometry data, and this is because chlorine has a very isotope pattern. But for tetrachloroethene, the pattern looks like this. Tetrachloroethene itself is going to echo the isotope. So the tetrachloroethene time series, we see something like this. There's tetrachloroethene itself. Here's the echoes. This is the pattern that we're looking to find this for compounds. So here's an example of one mystery. You you determine the chemical formula of this molecule. And if you type this into Google, find some suggestions for what it might be. It's actually a xylene substitute that's used in a lot of industry. So this is at least a speculation to the identity of the map, where we see enhancements of so it's all 7 drives all together this time. And if we want to investigate this compound further, a good tactic might be to take your sample right here, and then run it through GC offline later. Get a really good idea. Second target analysis, non-target analysis, is called comparative analysis. So this work was done by Madison Rutherford, who's a graduate student. And the idea here's pretty simple. Here's our raw data again. Each one of these red sticks represents an individual compound, but the tallest sticks aren't necessarily interesting or important. A lot of these are VOCs that are just present in the air all the time, and they're not related. So instead, we want to find, to make the really important or interesting VOCs pop out of this mass spectrum. We want to highlight the VOCs that are different in a residential area compared to the area around the wastewater plant, or area around the highway, or around the refinery. Isolate the region, find some boundaries for this area, and then pick one of the regions to be the reference, which we compare all of the other regions. We chose the residential neighborhood as a reference area. And we combine an average from all drives taken in that area. And then next, so what we do is we take the average measurement from one area and subtract it from the average measurement of the residential neighborhood. This gives us a difference spectrum. Show it as a percent difference so that the VOCs with high concentrations don't get visual. So in this difference spectrum on the bottom, any of you positive have higher concentrations in the area around the wastewater plant. And any of you negative and different are higher in the neighborhood. And then that it's some VOCs immediately pop out as being we see methane tile here, which we already discovered. So that's a nice confirmation that we're on the right track. This really big spike here is actually formic acid. We proposed some tentative IDs for other VOCs at high molecular weight. They might actually be okay. So we can also mass spectrum for the refinery compared to the neighborhood. And this is really complex spectrum. There's lots of VOCs here. And this rate pattern here, which I've highlighted, is instantly recognizable if you measure hydrocarbons with mass spectrometry. What we're picking up here is this fingerprint of hydrocarbon emissions from the refinery. Comparison of the area around US Highway 270 to the, there's not really a whole lot that sticks out. Mostly just acetaldehyde, which is probably from Koss. But what's really interesting about this plot is that nearly all VOCs have a higher concentration in residential neighborhoods than they do around the highway. So what that's telling us is that whatever this pollution is here in the neighborhood, it is not blowing off downwind from the highway. It must come from a source, highway. Next step is to take a look at interesting hotspots previously. And if you remembered, we identified one of these spots by looking at benzene hotspot. I also showed tetrafluoroethylene area. It turns out it's almost at exactly the same location. Investigate this hotspot, we're going to draw small box around just this area, and then use comparative analysis to find. And what we find is that this hotspot is absolutely really big spike here is xylene, which is this is toluene. Right? Xylene also in high quantities. We also measure tetrachloroethene, acetone, a lot of other hydrocarbons. There's some acetone around this hotspot, and concentrations of acetone being emitted from the off the chart. So next in our work, positive neutral fragmentation. So the idea is to take this very complex mixture of VOCs that come from many different sources, describe it instead as a smaller number of distinct sources, each of which has a composition. And we're using one called PMF. There's some toolkits available to do this, including one that's supplied by the EPA. And what PMF does is it takes this matrix of data, with all of the measures each time, and it decomposes it into 3 chemicals, each one of which has its own and has a unique chemical composition. So PMF, what it can do is suggest major compounds, help us find fingerprint or tracer compounds, and it can sometimes help reveal unexpected features that are a big part of the overall signal. But operates on total signal. It's not very good at picking up very small sources or things that are really transient. Guided PMF is really successful. Interpretation of the results does require some brain actually thinking about whether it makes sense and putting it in. So let's look at an example of PMF results. Restricted the data to the area just around a refinery. And PMF suggests there's 3 really distinct hydrocarbon mixtures that are being emitted in this area. So on the top, I'm showing the chemical profiles of these mixtures. I have a couple text labeled, one of them. And on the bottom is a map of the refinery showing where the hot spots of each are. So the red and blue mixtures have pretty high relative enhancements to aromatics, and they each have distinct hot spots. So there's one in location. Yellow chemical mixture has a lot higher mixture of really heavy alkanes. And its map shows a lot of more dispersed distinct. So we might speculate that these 2 mixtures are coming from refinery infrastructure, and this one might be from and that's typically distinguished by this really high molecular weight alkane. Okay, so here's a review of the workflow steps and what we discovered. So first, clarify goals. Then, just target compounds, include regulated species. Customer suggests already are out there. Protected compounds from new sources. Here I show the styling. Then, compounds in categories. Here I looked at methane trial from the wastewater plant. Then, analysis. First, search for chemically adjacent species, such as this mystery CFC compound. Then, helps us find other non-target compounds. Also look at interesting hotspots, and then characterization helps separate mixed sources and identify fingerprints. Finally, I wanted to return to the overall motivation of this project, which was supporting CDPHE's mobile measurement. So I did finish building and delivering this mobile app for them. And here it is in this very shiny Mercedes, which also seems to have gotten a little
I know the
squished.
pictures don't work.
Yeah, maybe it's just pictures of Mercedes Sprinter vans at this center. Problematic. Final keyword. We have 2 mass spectrometers, PCR. That is better than the one I used for the study, but smaller and has less resolution than Montrose's. And a very fast switching instrument for inorganic acids. We have a cards instrument from Caro, and a really nice sonic animal. Questions?
Question about your TCE history. Did you ever give us the source on that?
You know, so that's a good question. So if we look in the NEI, there is one emitter that is registered, that is at that location, which is a woodworking shop. I don't think that's what they actually do as a business, having driven by there many times. And also what they report is their emissions does not match at all with what we measured. So someone is cheating.
And the acetone is also coming?
Acetone is also
there?
coming from there.
Any speculation on what's going on?
Gosh, mystery place in neighborhood filled with junkyards that's using a ton of solvents. I'll let CDPHE figure it out.
Law
but we
enforcement
can-
hasn't been on this one?
Yeah.
Law enforcement isn't?
So CDPHE knows about this place now, right? And they have been driving their own van around at this point for a couple months now, and they do see that.
That's funny because I test out there too every
Yeah.
quarter. And we actually found it. The toluene.
I could see that too.
Was, I thought there was something wrong with the instrument. I've never seen it pegged that high before. It actually did, it listed, like Les said, it was so
Yeah.
high. We kept driving and they were painting outside the high pressure spray guns, semis, and everywhere. And there's a whole bunch of places like that in that area that do weird things.
Yeah, there's a bunch of weird stuff out there
And you're doing this for CDPHE for some?
for CDPHE. Maybe. You know, I don't know, and I will let someone who's not out there in a 2002 Honda CR-V figure.
I mean, tetrachloroethylene is a great stripper.
Yeah.
You can't use it anymore, but great for working finish stripper.
Yeah.
Did you find any source for the styrene?
So the styrene, I'm pretty sure most of that just comes from car exhaust. The buildup in the tunnel is a pretty clear indicator that it's coming from cars. That said, we do see a little bit of a hot spot around Sun 4 too. So I could absolutely imagine that as being for that hydrocarbon mixture that's coming out of their infrastructure.
You see it, but there's a polystyrene facility. Or I think it's, I'm gonna do that or Bill, where they have a lot of polystyrene sheets. And a lot of it's outside, and I get an increase every time I go by.
Yeah, there's a lot of industry in here. We didn't get everywhere. Like the pet food plant gets mentioned a lot of times. We didn't have enough battery life to investigate everything, so.
But we have tracked styrene from the polystyrene plant too.
Yeah, I could imagine
Or
that.
not manufactured, I think they just sheeted.
That food order to be a terrible.
The pet food place, everyone mentions it, and I wish we'd had a little bit more time to do it. Yes.
Upstate established direction.
Yes.
And you had baseline. You actually do away from upstream.
Yeah, yeah, exactly.
Yeah.
So can I jump to? Right. So here on this map, our general wind direction is going. And we can do this transect on US upstream, So that was sort of our baseline. And then the other baseline that we compared to was the drive from my house in Boulder to here, which was along US 36. Not really good experience. Going over the railroad tracks in Commerce City, that's a mile an hour. Yeah, they've got terrible road quality out there. But I mean, on the highway, I hit 100 kilometers an hour with. I think I have the land speed record.
Yeah, that's pretty fast, so.
But out here driving around in the 5 miles an hour. So ethylene oxide is tricky mass spectrometry because it's exactly the same chemical formula as acetaldehyde. So we can detect ethylene oxide and at pretty low detection limits, but it's very hard to say in ambient air if what you're detecting is acetaldehyde or ethylene oxide without any kind of extra context. So that said, we have done ethylene oxide studies. For example, we have a client in Germany, and they know that they have ethylene oxide that is emitted from certain locations on their facility. So when we drive through and see that chemical formula, like, sure, we know for sure that it's acetaldehyde or ethylene oxide. Now you can't tell that with the instrument, but logically, it's ethylene oxide.
As we're driving on all that TVX flags that they have.
Yeah.
That's-
Yeah, exactly.
that's certain.
Uh-huh. Yeah. So if we had, longer battery life, I mean, I was just running this off of a boat battery that was nailed into my car. We could have done, extra circles around that hotspot. But yeah, you can see the spikes in real time, which is also why you need another person sitting in the car running the instrument, because if you're the driver and you're really interested in mass spectrometry, like it is very tempting to be looking over the passenger seat with the spikes all the time. Focusing on the road.
We changed our policy because I almost wrecked ours twice.
Uh-huh.
Drive and watch. And you look up. So you gotta have two people.
Yeah, the CDPHE mobile lab, I made sure that you cannot see the you're sitting in the driver's seat. So they're gonna.
I think you were showing spikes. Air concentration. So like, you look at and still less than part millions. And so like I saw one chart that tends to.
Yeah, exactly. So, I spent a lot of time staring at benzene, so I do know those concentrations off the top of my head. And the tallest spike of benzene that we ever saw was 150 parts per billion. The background concentrations out there are somewhere between 100 and 400 parts per trillion, which is also pretty measured. And then the other spikes are kind of. Comments? Questions?
Thanks, Abigail. That's very interesting. Yeah, interesting. Yeah, I hadn't seen that small one. Yeah, I was gonna ask now.
100% did not. Okay. Yes.
fairly long bio. Short of it, or you want me to read?
I don't know what you got. But that's pretty long, yeah.
Yeah, let's see if we can.
I really don't.
I'll try to summarize.
Yeah, just like you can stop right there.
Yeah, okay,
You know,
okay. Yeah, sometimes when people write these bios, I don't think they realize that they're gonna be used by the monitor.
well, I think like our BD guy said, I need a bio, I'm like, just get it off the website. And then he,
Yeah.
So welcome to our next session.
how do I get this?
I'm Stephen Lazaro, Atmosphere Optics, I'll be moderating the session. I have everybody.
If you give me 2 minutes, I need to stop the recording of the session.
Sure, sorry.
Have Brian Catron, Spectrum, second presentation from Spectrum today. Brian has served as Spectrum's Director of Installed Systems